there's anything that you see that I have wrong, feel free to correct me. That's completely possible that I messed it up, so don't worry about it. Just speak up, and hopefully you'll help another person. And we do have a smaller group, so yeah, just feel free to jump in whenever you need to. Okay, so before we get started, just a couple of things to announce. So we are a volunteer organization, but just to cover some costs, we have a GoFundMe. So if you can afford some donations and you would like to, please do it. Don't feel obligated to, but that's there. And another thing is that Facebook group to find study buddies and just a community of people who are also studying for the MCAT, so you can feel like you're less alone in your journey. And lastly, if you have any questions at any point about missing any topic sessions and you want a recording, or just anything you want advice on starting to study for the MCAT, anything else, just email mcat101questions@gmail.com, and we'll try to help you to the best of our ability. So, does anyone have any questions before we get started with the actual topic session? Okay, so just to get started, we'll go over the terminology to hopefully break it down before we jump into the actual details. So SN1 and SN2 are two types of nucleophilic substitution reactions. So to break this down a little bit, nucleophilic means nucleus loving. So what this really means is that whatever this substance is, this nucleophile, it's going to seek out positive charge. And the reason for this is because it's electron rich and it's not stable with the electrons it has, so it seeks to give it away. So it seeks out a positive charge to neutralize its electron-rich nature. And substitution in this circumstance just means that you're initially going to start out with a compound that has one substituent on it, and after the reaction takes place, it's going to be replaced by another. And then next we have electrophile. So this is the substrate, sort of like the biggest compound. You have two. You have the electrophile, or this, which is the same thing as the substrate, and the nucleophile. So the substrate is the main reactant, and then the nucleophile is the second reactant. Usually this electrophile or substrate is an alkyl halide. I'm not going to explain too much what an alkyl halide is, but if anyone doesn't know or has forgotten, you can interrupt me whenever. And then the last thing that we need to talk about is a leaving group. So this is initially actually part of the electrophile or the substrate. So it's a substituent on that electrophile, but during the course of the reaction, it leaves that substrate and allows for the final product formation. So if you look at the picture on the bottom, this is an example of a nucleophilic reaction. The nucleophile in this case is an OH, and you can see that it has a negative charge, so that indicates that it has 3 lone pairs, so that's a good nucleophile. And then, I saw a question in the chat, what an alkyl halide is. Here's an example. So it's an alkane, so a saturated basic organic molecule, carbon-carbon molecule, and then an alkyl halide just means that one of the substituents is a halogen. So bromine is a halogen, so that this is an example of an alkyl halide. Does that help? Okay. And then, so to sum up, you have your OH here, which is a nucleophile, the electrophile, which in this case is an alkyl halide, and then your leaving group, which is bromine, which is initially a part of the alkyl halide. And then if you look at the product, you see that the Br is gone, and now you have an OH. Okay. So just another way to put this nucleophilic substitution is that we can look at the general form of the reaction. So you have that nucleophile with the lone pair of electrons. This could actually be a pi bond or any other form of electron-rich source. And then you have your leaving group, and which is part of the larger electrophile or substrate. And the products of this are the leaving group leaves and is separated. And then you have the nucleophile replacing the position of the leaving group in the electrophile. So what happens is that the leaving group is a weaker base than the nucleophile. So the stronger base, which is this nucleophile, is able to go in and attack this molecule to get the leaving group to leave. So that's a substitution that is referred to in the name of the reaction. So again, just to reiterate multiple times, the reaction will only occur if the nucleophile is more reactive than the leaving group. In other words, the nucleophile has to be more nucleophilic than the leaving group, and we'll talk about that in the next slide. So what it means to be a good or bad nucleophile is that there's certain properties that it has to meet. So good nucleophiles are electron rich. So they either have a free electron pair, like in some of these molecules in this picture. So OH has 3 free electron pairs. So does alkoxides that are negatively charged. Iodide has 4. And then another source of electron-rich substances are the pi bonds. So these are delocalized electrons. So that's another source of electrons that can be donated to the electrophile. So the nucleophile can be neutral or negatively charged, but the negatively charged nucleophiles are usually stronger or more nucleophilic than the neutral nucleophiles. And there's this word, just nucleophilicity, that refers to the strength of the nucleophile. So I just have here that it's a kinetic property, which means that it's a measure of how fast the reaction occurs. And I have this here just because nucleophilicity often corresponds to basicity, but basicity is a thermodynamic product, as in it tells you an equilibrium position. So that's just kind of a nuance that you don't need to worry about too much, but it's nice to know. Okay, and so nucleophilicity, or the strength of the nucleophile, is determined by various different things. So the first thing I briefly mentioned in the last slide is that charge. So nucleophilicity increases with increasing electron density, or more negative charge. And this makes sense because as long as you have more lone pair of electrons or more pi electrons to give off, the more reactive that substance will be. So for example, if we look at the very first example of water or a negatively charged OH, the OH is much, much more nucleophilic because the charge density, the electron density is much higher, so it becomes much more reactive. And it's the same thing with any of these examples. So the conjugate base will be the one that has an additional lone pair. And for that reason, the conjugate base is always a stronger nucleophile. Okay, so the next thing that determines nucleophilicity after the charge is electronegativity. So electronegativity is the tendency of an atom to draw electrons to itself. So nucleophilicity decreases as electronegativity increases. This makes sense if you think about the definition of nucleophilicity. So we define nucleophilicity as seeking out positive charge, but if you have electronegative atoms, it means they're trying to keep that electrons to themselves, so they don't want to go near positive charge. So for example, fluoride is the most electronegative atom on the periodic table. So um, if you go to fluorides starting at the same period in carbon, if that has a negative charge, carbon will be a negatively charged carbon is highly nucleophilic because it wants to get rid of that negative charge, whereas fluoride is stable with that extra lone pair of electrons, so it's less likely to react. And the last two factors that determine nucleophilicity, steric hindrance is the third one. So if you look at this picture on the right, steric hindrance basically refers to how bulky that atom is, or that substance is. So if you look on the way left, this atom that is the actual electrophile is pretty free in its surroundings, but if you look on the right, it's very crowded here. So what this crowdedness or bulkiness does is it limits the ability of this entire compound to properly attack the electrophile in the reaction. So the best nucleophiles are the least bulky. And the last one factor to consider is the solvent. So in nucleophilic substitution reactions, we only look at polar solvents because non-polar ones would not dissolve our reactants. So, but within polar solvents, we have polar protic solvents and polar aprotic solvents. So the biggest difference between these two is that protic solvents as opposed to aprotic solvents is the difference. So protic solvents can form hydrogen bonds. And what this does is it actually hydrogen bonds with our nucleophiles. So by doing that, it actually makes these nucleophiles less reactive. And we'll talk more about that in the next couple slides. So before I get to that, I have a question, and I'll release a poll. So I just have a couple of examples of nucleophiles, and if you can just try to pick which one would be a better nucleophile and what, based on what I just told you. And I'll talk to you as you go through it. So the factors to consider are charge, electronegativity of the atom, steric hindrance, and the solvent, which I told you is polar aprotic. And I'll tell you here, the polar aprotic solvent part doesn't matter too much here. So don't worry that much for now. Yeah, polar aprotic refers to the type of solvent that it's in. So that's coming up on the next two slides. But if you want to unmute yourself and ask a specific question, that's fine. If not, I'll just keep talking about it in the next two slides. So just hang on 1 second. I'll just end it here. So I think you guys should be able to see the results. Everyone mostly picked B. Does anyone want to share why? Okay, no worries.
I looked at the negative charge.
Yeah, go ahead.
I looked at the negative charge, and a nucleophile would want to give away that negative charge, so that's why I picked OH minus.
Yeah, perfect. Yeah, this was a pretty straightforward example, so I'll go to the next slide that has the explanation. So yeah, if we look at the specific if we look at option by option, NH3 does have a lone pair of electrons, so it can potentially act as a nucleophile, and same with water. It has two lone pairs on the oxygen, so it can also act as a nucleophile potentially. So, but these are both neutrally charged, so they're likely weak nucleophiles, whereas, like Akrita said, um, it has a negative charge, so it's more likely to be a stronger nucleophile. And actually, uh, ammonia, NH4 plus, is positively charged and has no lone pair. So, sorry, that's a typo. That should say it cannot act as a nucleophile. Any questions on that before we move on? Okay, so to
Real quick, I'm sorry, I just forgot the definition of a nucleophile. You said it was some wants to. It's because I missed the first slide.
okay, yeah. Here, let me go back quickly. A nucleophile is electron rich, so it has a rich electron density. So because of that, it tends to seek out positive charge. So the nucleophile literally translates to nucleus loving, and the nucleus is positive charge. So that's where that comes from.
All right, thank you.
Okay, so to talk more about the solvent effects, nucleophilicity in polar protic solvents increases down the periodic table. So this is because polar protic solvents participate in hydrogen bonding with the nucleophiles, so they kind of solvate the nucleophiles that you have, making them less reactive. And the reason why nucleophilicity increases down the periodic table in polar protic solvents is because the ability of hydrogen, of these atoms on the periodic table to hydrogen bond, decreases down the periodic table. So it's basically just like whichever atom is able to kind of evade that hydrogen bonding, it's able to stay the most reactive. So, and this is mostly referring to the case of the halogens. Like I have these other ones here, but the halogens are mostly the ones that show up in comparisons like this. So iodide is the lowest on in the group. So it's able to hydrogen bond the least. So because of that, it can stay the most reactive. And fluoride is the opposite. It hydrogen bonds the most with the polar protic solvent. As a result, when it's put in these polar protic solvents, it becomes the least reactive and becomes a weaker nucleophile as compared to the iodide. And just some examples of polar protic solvents here are water, alcohols, and carboxylic acids. So should I repeat that? This is a concept that shows up kind of frequently and is something that's personally confusing to me. So if you want me to repeat it, I can do
Please
that.
repeat that if you could.
Okay. So let me try saying it in a couple of different ways. So look at just these four atoms for now. Um, so if you can imagine a periodic table, it'll go fluoride on the top, chlorine, bromide, iodide. And what we're saying here is that iodide is the least able to hydrogen bond, and fluoride is able to hydrogen bond the most. So the problem with that is when these potential nucleophiles hydrogen bond, they're giving away those reactive lone pair of electrons. So because fluoride is able to hydrogen bond the most with these polar protic solvents, it becomes the least reactive when you put them in those specific solvents. On the other hand, iodide is able to escape that hydrogen bonding a lot more than fluoride can. So what this allows iodide to do is stay more reactive. It still has these lone pairs that are not reacting with the solvent. So it has these lone pairs still free to give away and react in the separate nucleophilic substitution reaction. Does that help, Lola?
Yes, thank you.
Thank you for asking. Okay, so in polar aprotic solvents, it's a lot simpler. So these are polar solvents, but they don't hydrogen bond. So there's no interaction between the solvent and the nucleophile. So as a result, nucleophilicity just correlates with basicity. So as a result, nucleophilicity just increases up the periodic table, and this is because fluoride is a stronger base than iodide, and basicity increases up the periodic table. And to take us back all the way to what basicity means, what a Lewis base is something that gives away a lone pair of electrons. So if you think about it, iodide is a larger atom, so when it has that extra lone pair of electrons, it's able to kind of hold on to that that extra density of the electrons a bit better. So it's just more stable. So it's less likely to give away those electrons. And compared to iodide, fluoride is much, much smaller. So it's really unstable with that extra lone pair of electrons. So it wants to give it away. And that's a definition of basicity, but it also is very close to what nucleophilicity is. So as a result, fluoride is a much stronger nucleophile when they're in a polar aprotic solvent. Any questions on what basicity is or anything that I just said? Okay, and then I have another question. So which of these reactions would proceed in DMSO? And this might be something that you saw in your class, but if you didn't, DMSO is just a polar aprotic solvent. So there's the hint. And I left this chart up here so you can refer to that. Let me release the poll. So now it probably feels like it's been a while since we talked about when reactions would actually proceed, but to remind you, the reaction would take place if the nucleophile is stronger than the leaving group, and the leaving group is part of the bigger substrate. So in this case, the substrate is this CH3F, CH3I, CH3Br, CH3Cl. So these are the substrates, and then these negatively charged ions are the nucleophiles. Yeah, so DMSO is just one type of polar aprotic solvent. So you really just need to know that DMSO is a polar aprotic solvent. So you're looking for when you have the polar aprotic solvent, essentially which of these atoms, so either the leaving group or the nucleophile, which is a better nucleophile. I'll end it in 10 seconds unless somebody actively wants me to give them more time, which is fine too. Okay, so we have most people pick B. Let me show. And that's correct. Does anyone want to give it a shot? Okay, no worries. It's a bit more difficult than the last one.
I chose B
yeah.
because you said a product, right? And that was like, you said it increases up the periodic table
Mhm.
or the group. So that's why I chose B.
Yeah, that's right. So, and then when the chat, Crystal said, because F is stronger than I in all the other answer choices, having a leaving group stronger than nucleophile. So yeah, when you mean stronger, we're talking about the strength of the nucleophile. And that's absolutely right that the leaving group cannot be a stronger nucleophile than the separate nucleophiles. So to look at it choice by choice. So to answer a question in the chat, DMSO is just a solvent. So whenever you have a chemical reaction, you need to be able to dissolve your actual reagents in something. So it's just the solvent. Does that make sense? Like usually you have water as a solvent, but that's a polar, well, water is one common solvent. So that's just a polar protic solvent. So when you want a polar aprotic solvent, DMSO is a common one. Okay, so it's not, in this case, it wasn't, it's pretty critical because that info you need to use to determine which will be a better nucleophile, if it's the I or the F, because if you had a polar protic solvent, the circumstance would be opposite. So when you're looking at these nucleophilic substitution reactions, it's actually pretty important to be aware of which solvent you're in. Okay. So yeah, to come back to this question, as both of you guys said, in polar aprotic solvents, the strength of the nucleophile increases up the periodic table. And this is consistent with because basicity increases up the periodic table, and for the reaction to occur, the nucleophile has to replace the leaving group. So whatever substance is on the right here has to be a stronger nucleophile than whatever is part of the substrate or the electrophile. So if we go back and look at each separate choices, in the case of F, we have that iodide is a weaker nucleophile than F, which is a leaving group in this circumstance. So that won't happen. And same thing with C, iodide is still the weakest, and bromine is just a little bit better. So better of a nucleophile. So iodine won't be able to replace bromine, and bromine is the second weakest after iodide, so it won't be able to replace the existing leaving group, which is chlorine. Okay. Any questions on that? So after talking about the nucleophile, the other important thing to talk about is the leaving group. So these are the groups that literally just leave the initial electrophile, which is the main substrate. So what these do to be good leaving groups, they have to retain the electrons after leaving the substrate. So when they leave, they take along. So in the initial circumstance, they're sharing a lone pair of electrons with the rest of the molecule. But when they leave, they take that electron pair. So they leave and retain a lone pair of electrons. So good leaving groups are able to stabilize these extra electrons and be unreactive. So if you have a bad leaving group and it does leave, it's just going to want to react again with the molecule that it left from. So it's not going to be able to act as a good leaving group. And what I have here is that conjugates of strong acids, so weak bases, are typically the best leaving groups. And to take us back repeatedly to the definition of acids and bases, so weak bases are ones that don't want to give up their lone pair of electrons. And this is because a good base is one that is able to donate a lone pair of electrons to the acid. So weak bases aren't able to donate that lone pair of electrons, and as a result, in the case of the leaving group, it's able to keep it to itself and be stable that way. Stable and be away from the electrophile. So and that stability with the extra lone pair of electrons increases with resonance and with inductive effects from electron withdrawing group. So if you remember what resonance is, this is just the electrons being delocalized throughout a molecule. So it's kind of able to prevent the lone pair of electrons just kind of like from settling in one place. And what this does is it gives it stability. And electron withdrawing groups are ones that want electrons from itself. So it's just another way to delocalize and stabilize the negative charge. And then on the right here, I have examples of good leaving groups. So chloride, iodide, and bromide are good leaving groups because they are weak bases. So if you remember, HCl, HBr, and HI are examples of strong acids. So these are conjugates of those strong acids, so they're weak bases. And then this molecule is a good leaving group because you can see that it has pi electrons, so it's able to participate in resonance. And that's another reason why it's a good leaving group. And then on the other hand, if you look at bad leaving groups, fluoride is a strongly basic atom. So we talked about how it was a good nucleophile because it's unstable with that extra negative charge and wants to give it away. So for that same reason, it's not stable with that extra electron, lone pairs of electrons it would get if it leaves. So it's a bad leaving group. And then OH is another example of a bad leaving group. Kind of like the same reason, it's a small molecule, it can't really keep that lone pair to itself and be stable. And just a simple question, which of these is the best leaving group? So think about which one's the weakest base, which one doesn't have resonance, which one is really small and can't stabilize that extra negative charge, just things like that. Knowing acid-base chemistry or knowing really well what it means to be acidic or basic is super helpful in these circumstances, because even if you can't specifically remember what a leaving group is, if you just know that it needs to stabilize negative charge, you can work through that once you have example molecules that you need to choose from. So that's like one hint just to work on your acid-base chemistry a lot. Specifically, the Lewis acid and base definitions. Okay, I'll stop it here. Have a little bit over half of you get it right. So it's good that you didn't pick OH because that's the most obvious one that's not a good leaving group. So just remember that the best leaving groups are weak bases. So weak bases won't react, and so they can keep that extra negative charge to itself and be stable. Sorry, hold on. Okay, yeah, I realize my B is different in this, but so I'll just go with explaining both of them. So fluoride is not a good leaving group because it's a strong base. It really wants to give away that lone pair of electrons. So, and same with CH3O or OH. These also are not stable with that extra negative charge, so they're not good leaving groups. And same with ammonia. Any questions on that? Yeah, this is a lot more about like testing your background knowledge on basicity. So that's another good area to brush up on if you find yourself struggling with these types of questions. Okay, so to jump into the actual specifics of what is a SN1 and SN2 reaction. So starting with SN1, the full name for this is the 1 refers to unimolecular, and the N is nucleophilic, and the S refers to substitution. So far we talked about what it means to be nucleophilic and about the substitution part of it. So now to talk about the unimolecular part of it. So this just means that the rate of this reaction depends only on one molecule. And this molecule, sorry to jump, but if you look at the bottom of the slide, this is just the electrophile. So the concentration of nucleophile that you have doesn't affect the rate. And this is because SN1 reactions occur in 2 steps. And the first step, which is also the rate limiting step, is the leaving group leaving and generating a carbocation. So I have an image on the next slide that'll explain it a little bit better, but just to explain why this causes the SN1 reaction to be unimolecular in terms of the rate reaction, the rate equation is because when you have a rate limiting step, the next step doesn't influence the rate as much. So whatever you have is that's affecting the rate is only the concentration of the electrophile, because the leaving group has to leave before the next step can occur. So the concentration of the electrophile that's containing the leaving group affects the rate of the entire reaction. And we'll talk about this more. It might not make so much sense here, but you form a carbocation and then form a product once the nucleophile attacks it. So the result is that you have a racemic mixture because your intermediate is a carbocation and it's a planar molecule. So what this means is that the nucleophile can attack on either side of it. So to take you to the actual image and go through it. So here's your rate limiting step. You have your leaving group here. It's going to fall off on its own and take that lone pair of electrons with it. And if it's a good leaving group, it's going to keep it and be stable. So here it is after it leaves. And then what becomes of this rest of this molecule is that this carbon becomes positively charged because it has 2 less electrons now because the leaving pair took that lone pair of electrons. So if you remember the definition of a nucleophile is electron rich and seeks out a positive charge. So the nucleophile is going to attack. And here's what I was talking about, the planar molecule. So the nucleophile is free to attack on either side of this carbon atom. And as a result, you're going to get 2 stereo chemistries of molecules. So one possibility is in the pink, it can attack on the left side and you have this stereochemistry, and then the other possibility is on the right and it can form this stereochemistry. So depending on what these substituents are, one would be R and one would be S. And it's important to know that these products are formed in a equal concentration. So it'll be 50% of this and 50% of this, just because whichever side this nucleophile will attack on is pure chance. And another word for this is a racemic mixture. So some questions? what makes a leaving group leave? So this is just the property of the group. So um, in some reactions, it can be the presence of acid or something else that makes it a better leaving group. But with strong leaving groups, they don't need much to leave. So it's just kind of the property of the leaving group itself. Does this have to do with Markovnikov? I honestly don't remember what that refers to anymore. Could you explain it a little bit more? I'll try to look it up really quick. Um, I think this is a little bit different. To be honest, I don't remember that rule too much, but I don't think you would necessarily, it's not the same thing. It's just more so referring to the fact that you have a planar carbocation, so the nucleophile is free to attack on both sides. I'm sorry, I can look that up for you if it's confusing and get back to you. Unless anyone else can jump in about that.
Yeah, I'm currently actually studying this right now in
Yeah, thank you.
OCHEM, so I could explain like the Markovnikov's rule. So basically, what I'm gathering from it is that the X in like HX, like the basically like the halide or the substitution, the substitute basically wants to bind to the most stable carbon, aka the most substituted carbon. So like it's gonna want to bind to a tertiary carbon more than like a secondary or a primary. And it's the opposite for hydrogen. So the hydrogen is gonna want to bind to the least stable or like the least substituted.
Yeah, that makes sense. Thank you so much, Hannah. Yeah, so in that case, as Hannah was explaining, you would actually need to have two places that, like two carbons to possibly react on, but in this circumstance, you just have one carbon to deal with. So it's a little bit different than Markovnikov's rule. This has to do with just kind of like spatial arrangements. So it's a little bit different. Yeah, thanks again. So the next type of nucleophilic substitution we have is a SN2. So the 2 refers to bimolecular rate reaction. So in this case, where in the last part, the rate only depended on the concentration of electrophile. Here, the concentration of nucleophile also matters, and that's because instead of having a rate limiting step and another step that follows it in SN2 reactions, it all happens in one step. So the nucleophile attacks at the same time that the leaving group leaves. So as a result, both the concentration of the nucleophile as well as the concentration of the leaving group containing electrophile both matter. And here is where it's a little bit different from the last part. We do have a stereospecific product forming. So whereas in the last one we have a racemic mixture, this product and SN2 reactions have an absolute stereochemistry that is the opposite of this stereochemistry of the reactant. So hopefully this picture will help a little bit more. So we had a question last time where someone asked, why does the leaving group leave? And I said that in strong leaving groups, they can kind of just go because that's what they prefer. But so in SN2 reactions, actually, the leaving group would leave after or at the same time as the nucleophile attacking. Sorry, it's actually at the same time that the nucleophile is attacking. So kind of like this attack is what makes that leaving group fall off easier. So to go through it step by step, you have the nucleophile here. attacking the carbon, which is not yet a carbocation. So in this reaction, we don't have a carbocation forming because all of this is happening at the same time. So bromine attacks, and then there's this brief moment where the chlorine, which is the leaving group, is still attached. So you have this very, very brief moment where you have a pentanary complex. So we have 5 substituent on that carbon. So another important thing to mention here is that the nucleophile attacks on the opposite side of the carbon that the leaving group is on. So this is called a backside attack. So after that brief moment where both the bromine and chlorine are attached, the chlorine quickly leaves. And as a result of that, you have the bromine lasting on the side of the carbon opposite to that of which the chlorine was on. So here, if you have a stereochemistry in which the chlorine's on the right, the bromine's on the left. So if we try to do RNS here, so chlorine's 1, the most priority, and the methyl is 2. So I guess this is S. Is that right? I don't know. Somebody correct me if that's not. So say that this compound has an absolute stereochemistry of S. If we look here, bromine is 1, this is 2, this is R, so you get a switch from S to R stereochemistry. So that's where you see that the stereochemistry has switched. Okay, yes, thank you for confirming. So this is one important or like clear indicator that separates SN2 reactions from SN1. So in SN2 reactions, you have a stereospecific product forming, and that stereochemistry is opposite of the stereochemistry of the reactant, whereas in SN1, you have both stereoisomers forming and they're in equal concentration. So typically when you write the reactants, you just instead of using dashes and wedges to denote actual stereochemistry, you just write these planar lines to indicate a racemic mixture. So hopefully that helps. Any questions before we move on? And sorry, I just noticed that we're getting a little close to 8. Sorry, I thought this would go a little bit faster, but if anyone has to leave, that's fine. I'll send out a recording to anyone who registered. You get that like tomorrow morning. And if you have any questions after watching the recording, feel free to ask me. Yeah, you're welcome. Bye, Crystal. Okay, so the next step is after going through the SN1 and SN2 reactions, now we have to look at if you have a reaction that you're given, and you're given the reactants, and you're given details like what the solvent is and what the nucleophile is, how do you go about determining if that's going to go through an SN1 reaction or an SN2 reaction? So there's a whole bunch of things to look at to get to that point. So I'll just go through these quickly and then go into detail. So the first thing is the substitution of that electrophile. So it's talking about how many substituents are surrounding that carbon that has that on the electrophile. And then the second is the strength of the nucleophile. So how good of a nucleophile do you have? Third is the solvent type. So we talked about polar aprotic and polar protic solvent. So that plays a big role. And then lastly, if the products are given and you see that there's inverted stereochemistry, that's obviously SN2. And then if you see that the products are not stereospecific, so they're just a racemic mixture, then you can pretty easily tell that it's SN1. But usually the products won't be given. So this 4 is just kind of like a bonus. Okay, so the first thing that's useful in determining if a SN1 or SN2 reaction is likely is a substitution of the electrophile. So if you remember, we talked about how the SN1 reactions go through carbocation formation. So on the other hand, SN2 reactions form through that pentacoordinate transition state. So when you look at SN1 reactions, they're more stable if they occur faster if the electrophile is more substituted. This is because, if you remember, more substituted molecules are able to stabilize that positive charge. So just in case if anyone has forgotten what tertiary, secondary, primary is referring to. So tertiary just means that the carbon has 3 more carbons attached to it. So in any of these cases, it'll first have a leaving group. So and then it'll have potentially other substituents, which are carbon substituents. It could also be other molecules like Cl, but like oxygens or anything else. But anyway, getting back to it. So to start from methyl will just have that leaving group. So in this case, bromine, and then just hydrogens. So no other substituents. Primary electrophiles, or alkyl halides in this specific instance, will have 1 carbon substituent, and then 2 hydrogens, and then your leaving group. Secondary, your leaving group, 1 hydrogen, and then 2 carbon substituents. Tertiary, your leaving group, and then all 3 remaining positions are occupied by substituents. So if you can imagine, if this bromine leaves as a leaving group and leaves that positive charge, these are methyl groups are electron withdrawing, so it's able to stabilize that. Sorry, not electron withdrawing. It's just simply the presence of these methyl groups is able to stabilize that extra positive charge because it's kind of able to like diffuse over that entire molecule, so it just brings stability. Whereas if you're looking at the methyl alkyl halide, there's nothing to stabilize the positive charge because the hydrogens don't really contribute any of those stabilizing effects. So SN1 reactions really favor tertiary or secondary alkyl halides to stabilize that carbocation. And then before I delve into the detail of the SN2 reactions, a quick trick is that this will always be the opposite. And to get into the... Does someone have a question? So this will be the opposite, and this is because the nucleophile has to attack the electrophile. So these, whereas in the SN1 case, these substituents were gonna act as stabilizing features. In SN2, they're kind of just like hindrances in the way. So they prevent the nucleophile from properly attacking. So you can kind of think of this as SN2 reactions needing easy access because that nucleophile has to attack. So in the case of a methyl alkyl halide, it's really easy because these hydrogens are really small and don't really bother the nucleophile or get in its way. So the nucleophile could easily just go here. And then on the other hand, if you look at the tertiary carbon, I know it's kind of hard to imagine, but these carbons are like bigger, at least really a lot bigger than the hydrogen. So I'm trying to circle it. I don't know if that's helping, but they kind of like block this position. And so the more substituted groups there are around that carbon, it hinders the ability of that nucleophile to attack on the backside of that electrophile. So for that reason, SN2 reactions really favor these methyl alkyl halides, and then primary, and then secondary, it's possible, but less likely, and then tertiary rarely can occur. And then SN1, to go back to those, tertiary is what it really favors, and then SN1s are possible with secondary, and then they basically can't happen. SN1 basically can't happen with primary and methyl alkyl halides because the carbocation is just way too unstable. So you can kind of think of it as like when you have a methyl and primary alkyl halide, you can be kind of sure that you're going to go through secondary, SN2 reactions. And when you have that tertiary alkyl halide, that'll almost always be SN1. The trickier one is just a secondary. This one can kind of go either way because SN1 and SN2 are possible with it. Okay, so to move on to the next factor, you also look at the strength of the nucleophile. So in SN2 reaction, the nucleophile has to attack the electrophile first. So these reactions need to typically have strong electrophiles. So if you remember what we talked about in the beginning, stronger electrophiles are ones that have negative charge. So CH3O with negative charge, CN, negative charge, OH. These are all really, really strong nucleophiles. SN1 reactions, on the other hand, can occur with weaker nucleophiles. This is because the leaving group has already left. So it's kind of like there's less effort needed to attack that carbyl cation compound. So SN1 reactions can happen with water, alcohol, so these are neutrally charged, so they're weaker nucleophiles. So the best way to think about this is that if you're going to have an SN2 reaction, you need a really strong nucleophile. So if you don't have that strong nucleophile, the only way that the reaction is likely to proceed is with SN1 reactions where you already have that easy access. Okay, and then the third consideration is a solvent type. So talked about this quite a bit earlier, but so SN2 reactions are initiated by the nucleophile attack, as we just talked about. So, so polar aprotic solvents don't participate in hydrogen bonding, so they don't hinder the reactivity of the nucleophiles. So, so they can favor that attack. So, because that nucleophile isn't reacting with the solvent and isn't being hindered in its reactivity, can go for that direct attack on the electrophile. On the other hand, SN1 reactions have polar protic solvents, and this is because when you're in that polar protic solvents, those nucleophiles are getting solvated and therefore are becoming less reactive. So in essence, they're becoming weaker. So it's kind of like if you go back to the logic of the strength of the nucleophile, if you don't have a strong enough nucleophile because it's getting solvated by the polar protic solvent, then you don't have enough of a chance to proceed to the SN2 reaction. So the only chance of that reaction proceeding is to SN1. Does that make sense? I feel like I may have confused you, so ask me to repeat it if you need it. Okay, we'll just try a practice problem then and see if that helps clarify anything. So last factor to consider is just the product stereochemistry. And this is something that you can really only use if the products are shown. So again, if product has a stereocenter, then you can be sure that the SN2 reaction has occurred. And then specifically, you should look for that inversion of stereochemistry to confirm if it's a SN2 reaction. And then if the product is shown to not have a stereocenter or stereospecificity, you can assume that it's a racemic mixture because you have an SN1 reaction and a 50-50 mixture of both stereoisomers have resulted. And then, so here's a summary of how to look for whether an SN1 reaction or a SN2 reaction is going to take place. So, well, this is just a rate law. It's not going to help you determine if an SN1 or SN2 reaction is going to take place, but this is where it gets the name of SN1 and SN2. So to move on to the other factors, to summarize it, SN1 reactions prefer tertiary and secondary alkyl halides, and they really don't occur with primary or methyl alkyl halides. SN2 reactions are the opposite. They prefer methyl and primary alkyl halides and can occur with secondary alkyl halides and then don't occur with tertiary alkyl halides. And then let me say this the other way around for the nucleophiles. So SN2 reactions, because you're going for a direct attack, you really need a strong nucleophile, and generally this will be negatively charged. On the other hand, if you don't have that and if you have a weak nucleophile, your best hope is a SN1 reaction. because you're not strong enough for that direct attack. So you're gonna want to wait until the leaving group leaves, and that occurs in an SN1 reaction. And the solvent is kind of like the same logic. If you're in a polar aprotic solvent, the reactivity of the nucleophile isn't messed with, so it can go for that straight SN2 attack. On the other hand, if you do have a polar protic solvent and it's weakening the reactivity of the nucleophile, then your best hope is an SN1 reaction. Yeah, Lupa, I will share this PowerPoint with you when I send out the recording, and that'll be tomorrow morning. Yep, welcome. And then polar aprotic doesn't involve hydrogen, so yeah, not that it doesn't involve hydrogens, but it can't hydrogen bond. So let me try to take you back to that very first slide. Here you have solvent effects. So if you look at these solvents, these are polar protics. So these are water, alcohols, things that can hydrogen bond. And these are polar aprotic. So these are polar, but they don't hydrogen bond. So they don't react or form hydrogen bonds with the nucleophiles and weaken their reactivity essentially. Does that help, Andrea? I'm not sure what's happening with the comments. If you guys have questions and you don't mind unmuting yourself and talking instead. Yeah, Kwan's here. So somebody said you couldn't access the recording. Yeah, I don't, which one are you talking about? This one isn't out yet. I have to wait until I actually end this session. So, and it'll be done encoding like tomorrow morning. So that's when I'll send it out. I don't know, does anyone still have questions? Okay, let's just try this question, and this is the second to last question, so we're almost done. So to proceed with trying to work out this problem, because you don't need to pull this as a multiple choice. So we have the leaving group, which is bromine, and you can recognize that because it's on this alkane. Well, this isn't actually an ether, but you can ignore this part for this reaction. So you have your leaving group on your electrophile, and you have ethanol water. So this is a polar protic solvent because ethanol and water can both hydrogen bond. And you have this NaCN salt, so and sodium cations, and then the Cn minus anions. So Cn minus is a strong nucleophile. So you have a good leaving group, a strong nucleophile, and a polar protic solvent. So I'll just go through it for the sake of time unless anyone wants to participate. Yes. So I'll say out what Kwan said because he's usually super helpful. So he said polar aprotic solvents favor SN2. The solvent does not hydrogen bond with the nucleophile. And polar protic solvents favor SN1 because the solvents stabilize the positive charge of the cation. Yeah, okay. That's a good point that I forgot to mention. So that's another reason why polar protic solvents favor SN1. Not only are the nucleophiles weakened, but when you have that carbocation intermediate, that's also stabilized, which is important for an SN1 reaction. Thank you, Kwan. And then another question was, can you describe how to identify if this is a secondary or primary structure? Yeah, so let's go back to that slide. So here's your primary and secondary. So you're looking at the carbon and it's attached to your bromine. And in the example, we have the same leaving group, it's also bromine. So to determine if it's a primary, secondary, tertiary alkyl halide, you just need to look at how many carbons this central carbon is attached to. So if we go back to this example, so here's your central carbon that's attached to your leaving group. And the only other carbon that the central carbon is attached to is this one. So that's one carbon substituent on that central carbon. So this is a primary alkyl halide. Does that make sense? Yes, it's primary. Primary one carbon cation on the central carbon. Okay, and then a while ago, somebody said that this is a SN2 reaction, and that is correct. So this one might be a little bit trickier because you have bits of conflicting information. So you do have a strong leaving group, which favors a SN2 reaction. No, it doesn't. Ignore that part for now. I'll come back to it. So you have a primary alkyl halide. So as we were just talking about, this primary alkyl halides really favor SN2 reactions. This is because the nucleophile can attack with a high degree of freedom, so there's not a lot of substituent blocking its way. And then on the other hand, if you try to consider why it can't be SN1, primary cations are really, really unstable when they, primary alkyl halides, when they form primary cations, carbocations after the leaving group leaves, it's really unstable. So SN1 reactions can rarely happen with primary alkyl halides. And then CN minus is your nucleophile here, and it's a strong nucleophile, so another factor that favors SN2 reaction. And then lastly, you have that the solvent is polar protic. So even though this is something that we said favors SN1 reaction because of one stabilizing the carbocation, primary carbocations are just so unstable that even if you have this polar protic solvent, it really cannot proceed. So your only option here is SN2. So this might not always be the case, but when you see a primary alkyl halide, SN1 reactions is basically not possible. And then just a note that I had about the product. So if you have an SN2 reaction, you might be looking for that inversion of the stereochemistry, but here you don't have dashes or wedges. So you may think that there's no stereocenter. Well, there isn't a stereocenter. That's because this original alkyl halide, so that your reactant didn't have a stereocenter because it doesn't have 4 unique substituent. So there was just no chiral center here. So that's why you can't imagine that inversion of stereochemistry. So don't be too confused by that. That whatever that backside attack did happen, it just so happens that this isn't a chiral center, so you can't envision that stereochemistry. Any questions on this? Okay, I have one more problem. So again, you have bromine as your leaving group. Can someone identify what type of alkyl halide this is? So here's your central carbon. Yeah, perfect. It's tertiary. So did you want to explain that, or? No worries. So you have your central carbon and it's attached to one carbon here. another carbon here, and another carbon here. So 3 carbon substituents. So it's a tertiary alkyl halide. And then what type of polar protic? Oh, I just said it, so never mind. So this is your solvent. So this is a polar protic solvent. And something interesting to note here actually is that you may notice that there's no separate nucleophile from the solvent. This is because this alcohol will act both as the nucleophile and as a solvent. So this is 1,2-ethanol. So does anyone want to guess if this is going to proceed through an SN1 or SN2 reaction? SN1. Yes, that's correct. Do either one of you want to explain why? Okay, no worries. So if we move on to the next slide, like you both said, yes, it is SN1. So it's a tertiary alkyl halide, so it strongly favors SN2 for that reaction. Sorry, SN. Okay, I have another typo. I'll fix these typos before I send it out. It should be Y's is SN1. So tertiary alkyl halides really favor SN1 reactions because it has a really stable carbocation. And then on the other hand, if you think why it can't be SN2, the hindrance from all these substituents is just too much for a SN2 reaction to be possible. And then moving on to the nucleophile / solvent, polar protic solvents also favor SN1 reactions. And then this is also your nucleophile. So if you look at it, it's a weak nucleophile. So that's another reason why SN2 is unlikely. So Hannah asks, is SN1 only tertiary, or could it be anything else? So it could also potentially proceed with secondary alkyl halides, and it doesn't really occur with methyl and primary. So for SN1 reactions, it's possible that they can occur with secondary or tertiary alkyl halides. SN2 can happen with methyl, primary, or secondary alkyl halides. Is that okay, Hannah?
Yeah, thank you.
Yep, thank you for asking.
I was wondering,
Yeah, go ahead.
for the MCAT, are we going to have to like, I forgot what it called, but like the steps. So like, is it more important to like, okay, I can have an idea, this is my reactant, and I can have an idea of this is the product, but are we going to really have to focus on now being able to draw arrows and yeah.
No, yeah, you don't need to know it because it's a multiple choice test.
Okay.
You don't have to do what you did in your orgo class,
Okay,
as long
thank
as you're
you.
able to like reason through it and consider your leaving groups, your alkyl halide substitutions, your solvents. Essentially more about predicting SN1 or SN2. You don't need to know the reactions in detail. It is good to know how it works in general, though.
Thank you.
Yeah. Okay. So just another last point that I want to mention about this is that here's your stereochemistry. So this is your first priority, second is third. So, or no, this is first, second, third. So I guess this would be R, but then you have your highest priority on a wedge. So this would be S. And then if you did priority rules for this, I guess it's 1, 2, 3. So R, S. So it looks like both are S. And that's not actually true. Because this is proceeding by an SN1 reaction, it should be a racemic mixture. So I just wanted to point out that this stereochemistry indicated by these dashes and wedges aren't exactly right. They should just draw plain lines to indicate that it's a racemic mixture. So that was everything. Does anyone have any questions about any of the slides that we discussed or in general?
So protic means that it can form hydrogen bonds, and aprotic is the otherwise.
Yeah, that's what it means in this context. Protic, Quan, correct me if I'm wrong, but that means like it's able to like release hydrogen ions in solution, right?
That sounds about right, though. Like,
Yeah. Yeah. In this context, it's just referring to the fact that it can hydrogen bond. Yeah.
Okay, thank you.
Yeah. And yeah, Raul, you'll get these slides tomorrow morning. When I'll email you a follow-up email. So
Also, really quick, will this recording be sent out?
yeah, so tomorrow in the email, I'll send you guys a follow-up email. It'll have a post-session form if you have any thoughts on how the session went and what I can improve on, and if you want to tell me what I did well. So that'll be in the email, and also the recording and these slides. And I'll get that out tomorrow morning just because this recording needs a little bit of time to be downloaded and everything. Anyone else have questions? But yeah, feel free to leave now if you need to go. Yeah, I'll keep working on trying to finishing in an hour. Besides that, just use this email mcat101questions@gmail.com if you have anything that you want to ask. If you revisit these slides another time and kind of get lost again. So any questions, just use that email.
I have another question about the material.
Yeah, sure.
So besides the like primary, secondary, tertiary, what are the most important things to look for when you're trying to identify whether it's an SN1 or SN2?
Yeah, that's a great question. And most of the MCAT questions that are about these reactions would hinge a lot on determining if you think it's going to go through SN1 or SN2. So this chart contains most of the things that you should look for. I think looking for whether it's tertiary, secondary, primary, or methyl is kind of the easiest first step, because if it's tertiary, then you can pretty quickly get rid of it proceeding through an SN2 reaction. On the other hand, if it's primary or methyl, you can eliminate SN1. So de Quante usually boils down to carbocation stability or steric hindrance. Yeah, so you're kind of like weighing which of those is most likely to occur. So if you're looking at carbocation stability, then your SN1 is most likely, and then if you are looking at SN2, then you need to have like less steric hindrances. But yeah, that's like a quick way to look at it. I guess it's just like practice. If you keep working through problems, yeah, I don't really know if it's a short way. It's more about like understanding what these two mechanisms really proceed by. Yeah, so
Okay.
carbocation stability is important for SN1, and then stereochemistry for SN2.
So it's like the less steric hindrance, the more likely it's SN2.
Yes, yeah.
Okay, I see. Is steric hindrance the same as steric strain?
I don't super remember what steric strain is. I don't think they're the same thing.
It's like a methyl cloud, you know, like how the methyl clouds are interacting. So I feel like a steric hindrance, I just haven't heard hindrance, but is it like the same thing?
Sorry, I'm just like trying to quickly look at it.
Yeah.
Correct me if this definition is wrong, but it says it's steric strain is the repulsion between like two adjacent like substituents. Whereas steric hindrance is more so referring to the fact that you need the nucleophile to attack that central carbon, and when you have bigger substituent, it's getting in its way. So it's a little bit different because steric strain is referring to like how two adjacent substituents are interacting, whereas steric hindrance is referring to the fact that just by these substituents being there, it's getting in the way of the nucleophile.
Oh, okay, I see.
On foot.
Makes sense.